Now we want to talk about specific heats for gases. And to start that discussion, I want to look here at this formulation of the ideal gas law that we had before. Notice here I've got the average kinetic energy. For an ideal gas where the particles don't interact and there are no potential energies, this is the total energy for a particle. So if I want the total energy of the gas, I just take N times that average. In other words, E internal is equal to N K average, which is equal to 3/2 N K Boltzmann T, which is also 3/2 N, that's a little n, R T. So the energy only depends on the number of moles present and the temperature. It doesn't depend on the volume, it doesn't depend on the pressure, it doesn't depend on anything other than the number of moles and the temperature when we're talking about the internal energy of an ideal gas. That is this statement right here. The internal energy, E internal, of an ideal gas is a function of the gas temperature only. It does not depend on any other variables. So that's one interesting thing that we come to. Another interesting point. This is a part of the table of specific heats that we saw in Chapter 18. And you'll notice that the specific heats per unit mass are really very different. Lead and tungsten are fairly small, a little bit higher for silver and copper, very high for aluminum. But if we look at the specific heat per mole, they're all almost identical. So something interesting is happening. So maybe when we talk about specific heats, it will be helpful to quantify it based not on the mass of a material present, but on the number of moles present. That's what we're going to do now for an ideal gas. And there will actually be two specific heats, one for constant pressure and one for constant volume. We'll start with the constant volume one first. So let's try and find our specific heat for a gas that's at constant volume. So here's our gas in the cylinder, and we've placed pins here and here. So even though the pressure may increase, that pressure will never increase the volume. What's important is that means that the change in temperature happens on a vertical line here on the PV diagram, so that there's no area underneath and no work done. Now a specific heat before was the heat was equal to M specific heat for mass times delta T. To be a molar specific heat, we change this from an M, a mass to quantify how much stuff I have, to a lowercase n, the number of moles. So we're looking for something that says the heat is equal to N times the specific heat at constant volume times the change in temperature. We've just pointed out that this is a situation with no work, which means the change in internal energy, which is equal to heat minus work, is just the heat because the work goes to 0. And I have a formula for the internal energy. The internal energy is simply equal to 3/2 N R T. Well, as I add heat, N and R aren't going to change, so the change in internal energy is simply equal to 3/2 N R delta T, and that's equal to the heat, Q. Well, here's the N that we had right here. Here's the delta T that's there. Whatever is left had better be our specific heat. So we find that the specific heat at constant volume is equal to 3/2 R, where R is the ideal gas constant, 8.31 just 8.31 joules per mole Kelvin. let's compare that to some real data. We find that for a monatomic gas, the ideal, as we said, is 3/2 R times, which is 12.5 joules per mole Kelvin. For helium, that's almost exactly right, and even for argon, it's not very far from being correct. It's 12.6 instead of 12.5. We'll talk in a minute about why these are different for diatomic and polyatomic gases. There's actually a very simple explanation for that, which we will come to in a moment.